Welcome. This presentation explores the various degradation threats affecting cooling and heating medium systems. These threats can compromise system integrity, safety, and performance if not properly managed. This diagram referred to Corrosion Threats Handbook, Upstream Oil and Gas Production Plant by Energy Institute. Introduction: we'll focus on understanding the types of degradation, where they occur, and how they affect system reliability. This knowledge is essential for effective inspection and maintenance planning. Cooling and heating systems are critical in industrial processes for temperature control and energy efficiency. System degradation can lead to operational downtime, safety hazards, and increased maintenance costs. Objective: identify key degradation threats and understand their mechanisms and impacts. System overview: understanding the layout and function of each component helps us identify where specific threats are most likely to occur. Cooling medium system: in this diagram highlighted with blue color line, it uses water or glycol-based fluids to absorb heat. Heating medium system: in this diagram highlighted with red color line, it uses steam, oil, or other fluids to deliver heat. Key components of the cooling and medium system are the following. The first is expansion vessels. Accommodate fluid volume changes due to temperature. The second is heat exchangers, transfer heat between process and medium. The third is circulation pumps, maintain fluid flow through the system, and the fourth is waste heat recovery units, improve energy efficiency by reusing heat. Internal threats: these threats are internal and often hidden, making them difficult to detect without proper inspection techniques like ultrasonic testing or fluid analysis. The most common internal threats occur are the following. Number 1 is oxygen corrosion, or O2, occurs when dissolved oxygen reacts with metal surfaces, forming rust. Number 2 is microbially influenced corrosion, or MIC, caused by bacteria that produce corrosive byproducts. Number 3 is galvanic corrosion, happens when dissimilar metals are electrically connected in a conductive fluid. Number 4 is weld corrosion, localized corrosion at weld joints due to metallurgical differences. And number 5 is crevice corrosion, develops in stagnant fluid areas like gaskets and flanges. External threats: external threats are often underestimated. CUI is particularly dangerous because it progresses unnoticed until insulation is removed. The most common external threats occur are the following. Number 1 is external corrosion, caused by environmental exposure, especially in humid or coastal areas. Number 2 is corrosion under insulation, or CUI, moisture trapped under insulation leads to hidden corrosion. And number 3 is fatigue and fretting, or FF, mechanical wear from vibration or movement between surfaces. Pump-specific threats: pumps are critical components and are highly susceptible to erosion. Monitoring flow rates and using wear-resistant materials can help mitigate this threat. The most common pump-specific threats occur is erosion corrosion, caused by high-velocity fluid carrying abrasive particles, common in pump impellers and casings, accelerated by cavitation and turbulence. Additional threats: these threats may be less common but are severe when they occur. They often require specialized inspection and mitigation strategies. The additional threats may occur are the following. Number 1 is carbon dioxide corrosion, or CO2, forms carbonic acid in water, leading to metal loss. Number 2 is hydrogen sulfide corrosion, or H2S, produces sulfide scales and embrittlement. Number 3 is grooving corrosion, localized attack forming grooves along flow paths. Number 4 is stress cracking, or SCC, cracks due to tensile stress in corrosive environments. Number 5 is liquid metal embrittlement, or LME, brittle failure due to liquid metal penetration. And number 6 is acid corrosion, caused by low pH fluids attacking metal surfaces. Visual summary: this visual helps consolidate our understanding. Use it as a reference during inspections to prioritize high-risk zones. In this diagram highlighted the following: internal threats, corrosion types inside vessels and exchangers; external threats, insulation and environmental exposure; and pump-specific threats, erosion zones. Red-marked areas indicate major risks. Mitigation strategies: a proactive approach combining design, monitoring, and maintenance is key to minimizing degradation and extending system life. Here are the mitigation strategies to follow. Number 1 is material selection, use corrosion-resistant alloys and coatings. Number 2 is protective coatings, apply epoxy or polymer layers to exposed surfaces. Number 3 is inspection monitoring. Use NDT methods and fluid sampling. Number 4 is environmental controls, manage humidity, insulation, integrity, and fluid chemistry. Number 5 is flow management, avoid high velocities and turbulence in pumps and piping. Inspection methods for internal threats. This summarizes the most effective inspection techniques for internal threats. Many of these methods are non-intrusive and can be integrated into routine maintenance schedules. When the threats is oxygen corrosion or O2, then the inspection methods to use for detecting the threat are UT or ultrasonic thickness, radiography, corrosion probes and oxygen monitoring. When the threats is microbially influenced corrosion or MIC, then the inspection methods to use for detecting the threat are microbial or sulfate sampling, UT, radiography, biostuds, sidestream monitoring. When the threats is galvanic corrosion, then the inspection methods to use for detecting the threat are UT, radiography, visual inspection, material compatibility checks. When the threats is weld corrosion, then the inspection methods to use for detecting the threat are UT, radiography, online monitoring with welded probes. When the threats is crevice corrosion, then the inspection methods to use for detecting the threat are visual inspection during maintenance, UT, gasket and clamp checks. Inspection methods for external threats. This summarizes the most effective inspection techniques for external threats. Many of these methods are non-intrusive and can be integrated into routine maintenance schedules. When the threats is external corrosion, then the inspection methods to use for detecting the threat are visual inspection, ROV for subsea, CP potential monitoring. When the threats is corrosion under insulation or CUI, then the inspection methods to use for detecting the threat are strip and search, thermography, pulsed eddy current, real-time radiography. When the threats is fatigue and fretting or FF, then the inspection methods to use for detecting the threat are visual inspection, radiography, vibration monitoring, stress analysis. Inspection methods for pump-specific mechanical threats. These threats often require specialized inspection tools. Early detection is key to preventing catastrophic failures, especially in high-risk zones like pumps and other mechanical equipments. When the threats is external corrosion, then the inspection methods to use for detecting the threat are UT, radiography, acoustic probes, erosion coupons, flow monitoring. Inspection methods for chemical miscellaneous threats. These threats often require specialized inspection tools and chemical monitoring. Early detection is key to preventing catastrophic failures, especially in high-risk zones like chemical injection points. When the threats is CO2 corrosion, then the inspection methods to use for detecting the threat are UT, radiography, corrosion probes, intelligent pigging. When the threats is H2S corrosion, then the inspection methods to use for detecting the threat are UT, dye penetrant, eddy current, radiography. When the threats is grooving corrosion, then the inspection methods to use for detecting the threat are intelligent pigging, UT, flow parameter monitoring. When the threats is stress corrosion cracking or SCC, then the inspection methods to use for detecting the threat are dye penetrant, eddy current, UT, chloride monitoring. When the threats is liquid metal embrittlement or LME, then the inspection methods to use for detecting the threat are dye penetrant, MPI, or magnetic particle inspection. When the threats is acid corrosion, then the inspection methods to use for detecting the threat are UT, radiography, corrosion probes, chemical analysis. Detailed summary of key degradation threats. When the threats is oxygen corrosion or O2, it causes oxygen dissolved in water reacts with metal surfaces. The occurrence of this threats is common in aerated water systems, especially where leaks or poor deaeration exist. The susceptible areas of this threats is pipework, vessels, welds, and under deposits. The mitigation strategies for this threats is oxygen scavenging, leak prevention and mechanical deaeration. The inspection method for this threats is UT or ultrasonic thickness, radiography and corrosion probes or coupons. When the threats is microbially influenced corrosion or MIC, it causes sulfate-reducing bacteria in stagnant, deoxygenated environments. The occurrence of this threats is deadlegs, under deposits, mothballed systems. The susceptible areas of this threats is water injection, firewater, drains, seawater systems. The mitigation strategies for this threats is biocide treatment, deadleg removal or drainage. Circulation and risk-based inspection. The inspection method for this threats is microbial sampling, UT, radiography, biostuds, or side stream monitoring. When the threats is galvanic corrosion, it causes electrical contact between dissimilar metals in a conductive fluid. The occurrence of this threats is welds, gaskets, pumps, nickel-plated components. The susceptible areas of this threats is seawater systems, hydrocarbon systems, under insulation. The mitigation strategies for this threats is material compatibility, insulating gaskets or spools, sacrificial coatings or cathodic protection. The inspection method for this threats is UT. Radiography, visual inspection. When the threats is weld corrosion, it causes metallurgical differences between weld and base metal. The occurrence of this threats is poor weld quality or morphology. The susceptible areas of this threats is pipelines, flow lines, systems with CO2, O2, or acid exposure. The mitigation strategies for this threats is proper weld procedures, corrosion inhibitors, and quality control during fabrication. The inspection method for this threats is UT, radiography, and welded probes. When the threats is crevice corrosion, it causes differential concentration cells in stagnant fluid zones. The occurrence of this threats is gasket interfaces, clamps, bolted joints. The susceptible areas of this threats is seawater systems, flanges, instrument tubing. The mitigation strategies for this threats is material selection, weld overlays, temporary preservatives, wax, grease. The inspection method for this threats is visual inspection during maintenance, UT in suspected zones. When the threats is erosion corrosion, it causes high-velocity flow with abrasive particles. The occurrence of this threats is pumps, bends, valves, impingement zones. The susceptible areas of this threats is recirculation pumps, flow obstructions. The mitigation strategies for this threats is flow control, sand management, and erosion-resistant materials. The inspection method for this threats is UT, radiography, acoustic probes, erosion coupons. When the threats is corrosion under insulation or CUI, it causes moisture trapped under insulation. The occurrence of this threats is damaged cladding, degraded seals. The susceptible areas of this threats is warm/hot pipework, vessels, heat-traced components. The mitigation strategies for this threats is dry insulation, effective coatings, avoid insulation where possible. The inspection method for this threats is strip and search, thermography, pulse eddy current. Top 10 frequently answer in questions of degradation threats to cooling and heating medium systems. Question number 1. What are the most frequent degradation threats in cooling and heating medium systems? The answer is, the most frequent threats include, oxygen corrosion or O2, microbially influenced corrosion or MIC, galvanic corrosion, weld corrosion, crevice corrosion, external corrosion, corrosion under insulation or CUI, and erosion corrosion especially in pumps. Question number 2. How can I detect corrosion under insulation, CUI? The answer is, CUI is detected using strip and search inspections, thermography to identify wet insulation, pulse eddy current testing, real-time radiography, and focus on warm pipework and damaged cladding. Question number 3. What inspection methods are best for detecting internal corrosion? The answer is common methods include ultrasonic thickness or UT measurement, radiography, corrosion probes and coupons, and intelligent pigging for pipelines. Question number 4. How do I identify erosion corrosion in pumps and piping? The answer is, use the UT and radiography for wall thinning, acoustic monitoring for flow turbulence, erosion probes and flow rate analysis, and look for signs near bends, impellers, and high-velocity zones. Question number 5. What causes MIC and how is it monitored? The answer is, MIC is caused by bacteria in stagnant, deoxygenated water. Monitoring for this threats includes microbial and sulfate sampling, UT and radiography, and biostuds or side stream monitoring. Question number 6. How can galvanic corrosion be prevented? The answer is, prevention strategies: avoid dissimilar metals in contact, use insulating gaskets or spools, apply sacrificial coatings and select compatible weld materials. Question number 7. What are the signs of weld corrosion and how is it inspected? The answer is, signs include localized thinning or pitting near welds. Inspection methods can be used are UT and radiography, online monitoring with welded probes, and visual inspection of heat-affected zones. Question number 8. What makes crevice corrosion difficult to detect? The answer is it occurs in hidden areas like gaskets, flanges, and clamps. Detection relies on visual inspection during maintenance, UT in suspected zones, and material and gasket selection reviews. Question number 9. How do I prioritize inspection zones in these systems? The answer is, use risk-based inspection or RBI to focus on high-risk areas such as pumps, welds, insulated zones. Analyze historical data and degradation trends. And combine UT, radiography, and chemical monitoring. And the question number 10 is, what are the best practices for mitigating degradation threats? The answer is, best practices include selecting corrosion-resistant materials, applying protective coatings, managing flow rates and turbulence, regular inspection and monitoring, and controlling environmental exposure and insulation integrity. Thank you.